Unit 2, Lesson 3, the name game. In this lesson, we were asked to look at different functions from different points of view. One of the things that we want to make sure we solidify is, do you know the difference between discrete or continuous? And also, we start talking about determining the domain of a function. So as we look through these examples, we're going to really narrow in on those topics only. So here's a function. This function is giving us clues that it is a linear function. For one thing, x is to the first power right here. That's just x to the 1. But it's x and y. And there's no restrictions given. So we're going to say that this is a continuous function. And as far as the domain goes, that would mean what kinds of numbers can you input into this function? And really, any kind of number will work. Fractions, decimals, percents. So we'll just say that the domain for this is all real numbers. Let's look at our next one. Now, you might recognize this. This is a geometric sequence. It's geometric, and in fact, you're given the recursive form of it here. The explicit form would look like f of n equaling 1 times 2/3 to the n minus 1. Well, that is not continuous. That is discrete. And the reason is, our inputs can only be the numbers 1, 2, 3, 4, 5, and so on. Because we're talking about the first number, the second number, the third number. So the domain of this would actually be the counting numbers, or also called the natural numbers. The shortcut for that is just the letter N, and we'll just say natural numbers. The type of function, again, geometric. Now here we're given x and f of x. So if you haven't noticed by now, x is used for continuous functions. N is used for discrete functions. What's going on here might be described as, for example, you're underwater. You're negative 130 feet underwater. And the f of x is the amount of pressure that water is putting on you. So as you get closer to 0, the pressure is getting less and less. That means that the domain of this function, if the story started at negative 130, it would end when you get to the surface of the water at 0. So this is all reals, but only in a specific interval. So all reals between negative 130 and 0. If, for example, that is what the story is. Now, when you're given a graph, a good way to know if a function is continuous or not is, can you trace it out with your pencil, never lifting your pencil off the paper? So can we trace this function never having to lift our pencil? And you'd have to say yes. So this is continuous. And really, this thing could go on forever, to the left or to the right. So the domain here would be all real numbers. These kind of functions are called exponential. So when they are continuous and they are growing with some sort of a factor, there's a multiplication involved, exponential. Now this one is also exponential, but there is a definite starting point here. And then it sort of trails off at the top. So although it's continuous, because we can connect it together with a nice smooth curve, we could say that the domain is all reals greater than 0. Let's contrast that here. Here's a function in words about a bubblegum machine. It's filled with 500 candies, and a person puts in money and 10 candies come out. This function is a model for the number of candies left in the machine after a person buys some candy. You could represent this as a table. In fact, let's not use x. Let's use n and f of n. No persons, 1 person, 2 persons, 3 persons. 500 candies, then we're going to lose 10, then we're going to lose 10, then we're going to lose 10. So this is definitely arithmetic. We are subtracting 10 each time. And it's going down by 10. So that's the difference. The domain is not every number, not all real numbers here. If you look on your chart, these are whole numbers. So they start with 0 and they go up. In fact, they go up until basically the candy machine is empty. So we'll just say whole numbers for now. It would be discrete. We don't have in-betweens. There's no in-betweens on the number of people, and there's no in-betweens on the groups of 10 candies. Okay, here's another story problem. A radioactive element decays at a rate of 5% each year. The scientist begins with 40 grams of the element. The function is a model for the amount of the element remaining at a given time. So what happens in radioactivity is you've got these atoms all clumped together, and they are so energetic that they are shooting off pieces of themselves randomly every now and then. And when those particles hit, for example, the human body, they destroy the cells that they go through. So radioactivity is usually bad for people. And it also is a loss of mass. So everything is getting lighter and lighter as time goes on. Well, what kind of a function would this be? Would this be discrete or continuous? Well, it kind of depends on how you look at it. Because, yes, we can go in between the times, but we are losing specific numbers of atoms. The thing, though, about that, and this is like a previous problem we talked about in our last lesson, it depends on how much you zoom in. So really, there's no harm in calling this function continuous. Okay, in fact, we could model it as f of x equals 40, we're starting with, we're losing 5%, but that means we're retaining 95%. And we're starting at time 0. So that would be to the x. It's continuous. And the domain, well, if you think about it, we're starting at time 0. So the domain is all real numbers, well, basically starting at 0. This is exponential, definitely. The growth factor is 0.95. So actually it's not growing, it's shrinking, it's getting smaller. This function is a sequence. It's jumping from point to point. In other words, I have to pick up my pencil to go from one point to the next point to the next point. So this is discrete. The domain of the function, the x values, 0, well, you can't see it, but it's there, 0, 1, 2, 3, 4. This one seems to stop at 4. So the domain, I could list out the numbers exactly. It's 0, 1, 2, 3, 4. Those are the only allowable inputs that I see on this graph. Now, there might be others that I just can't see. In that case, I would probably call this whole numbers as my domain. Okay, it looks like you're increasing the distance from point to point as you go up. It's going up faster and faster. So my guess is this is going to be geometric. And the growth factor, you can estimate it. Let's see, they're separated by 1 here, then they get separated by 2, then by 4. That seems like a doubling. That seems like the growth factor would be 2. Okay, this is a continuous curve. You say, well, it's not a curve, it's a straight line. Yeah, I know. I call it a curve if it's connected. It's continuous, definitely. Doesn't seem like it needs to stop anywhere. This domain can be all real numbers. And by the way, there is a shortcut for that. It's the letter R. In fact, a lot of textbooks like to write the R this way. Type of function, linear, and it has a slope. It doesn't have a growth factor. So it has a difference. It's kind of hard to estimate the difference here, but if I pick maybe this point and this point, that looks like a rise of 10 and a run of 3. And we're going down, so it's negative 10. So probably around negative 10/3. A little over negative 3. So let's talk about some of our takeaways. How do I identify what kind of a function that we have? Well, you know that arithmetic sequences are linear. Okay, so arithmetic are linear. Geometric ones, geometric sequences, when they are continuous, they are exponential. We'll just say exponential-like. And so that's linear versus exponential. Discrete versus continuous. Remember, if you have something like dot, 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 that's discrete. And if you have something connected together, That's continuous. All right, well, that's it for now. See you next time.